Okay, so today we're going to be discussing convolution, which used to be the primary way AI systems encoded images of the world, and still is today in many cases. So how does convolution work? Let's go through the base idea first. Okay, so the base operation of convolution is we're going to take our convolution kernel and basically shift it across our image, an element-wise multiply, and then add the sums at every pixel or position to create a new value. So as we move our convolution kernel, this would be the first interpose, right? So at that position, we're going to get 1 times 0, okay? And we're going to get negative 1, also times 0, and we're going to get negative 1 down here, times 0 down here, and we're going to get 1 here, times 1 here. And then we sum up all the values to get our output value here, which we place in our activation map output here. So that's literally the operation of convolution. And in this example, we would basically shift our kernel across the image 4 times. So 1, 2, 3, 4. Just like that. And once we do that, we would get our activation map down here. So 4 convolutions, 4 output values in our activation map. Okay, so now that we know how to do a convolution, if we remember, we take this convolution kernel and we slide it across our image like this, right? And then we calculate values. We can start to attempt to build the core intuitions behind why we care about convolution and what it's actually doing for us. At least in the first layer, let's say we're talking about a CNN. In the first layer of convolution, when we're convolving on our image, each kernel is capturing a feature in our image. So I've drawn out 2 examples. Let's say this kernel is capturing a vertical line. It's looking for vertical lines in our image. And this kernel is looking for feature 2, or horizontal lines. So these respective kernels are looking for vertical lines and horizontal lines respectively in our image. And you can kind of look into the history of kernels and how people used to make them to understand how this kernel captures a vertical line and how this one captures horizontal lines. I won't explain that here, but hopefully you can kind of see how ones and negative ones are arranged differently to kind of look for these different features. And you can see in our image we actually do have a vertical line as well as a horizontal line here. Anyways, so the core intuition is that, at least in our first layer, our kernels are looking for features in our images respectively, okay? After those convolutions in our first layer, we get these activation maps that are basically feature detections in our image, okay? So you can kind of see that, hey, we've found some kind of, horizontal line thingy here, and similarly we found some kind of vertical line in the image as well. So our convolutions are correctly detecting the features we want, okay? So we have, each of these activation maps, and while I've only drawn out 2, you can do this you can have 4 different kernels, you can have 16, even 32, okay? So you can have, and you can have more than that actually. So after you get all of these feature maps, generally in a CNN, we stack them up into tensor form. So we have this stacked up feature map, okay? So that's the output of our first layer. Now, say we want to convolve again, right? So this would be like the second layer of a CNN. What would we do? Well, now we have a tensor, so our convolution kernel also needs to be, in tensor format. So it needs to have the same amount of layers. And basically, we do the same thing. We're going to convolve in this same way, except with more dimensions, okay? So basically, we're convolving like this now, just to kind of illustrate what's happening. It's the same thing, just with more dimensions. So as we do that, and again, you can have any number of kernels, except now that we're deeper into the network, we're not looking for features in our image anymore, right? Because we're convolving across our feature maps from the previous layer. So we're not convolving on the image anymore. We're convolving on feature detections. So now that you do this, what you're actually picking up with the second layer of convolution is combinations of features, right? In our first layer, we were detecting things like horizontal lines and vertical lines, right? Feature 1 and feature 2. Well, now we're looking for combinations of those features. So what's a potential combination of a vertical line and a horizontal line? Well, it'd be like a corner, right? Or even like a right angle. Or any number of things, right? A vertical line and a horizontal line can make a lot of different things. But the point is, in our second convolution, we're now looking for combinations of features, okay? Things like corners. And so it's the exact same thing as above. We're going to convolve, n amount of times to get n number of feature maps, okay, here. And then they're going to get stacked again because deep learning uses tensors. And so now we're going to have this stacked up feature map of feature maps, okay? And as you get deeper and deeper into your network, the key intuition is that you're going to start to detect combinations of features, right? So in layer 1, we were looking for things like vertical lines or horizontal lines. In layer 2, we're looking for combinations of these features, right? And as you get deeper and deeper, layer n, you're starting to look for things like combinations of combinations, right? So maybe two corners combined to form a square, right? If you get deeper even, maybe you're looking for faces or even automobiles, right? So what's really important to understand is that anything visible in this world is kind of combinations of lines, really. Your smartphone, your car, your jacket, these are all just combinations of contours and lines. And the idea is that our CNNs now are capable of understanding complex combinations of features. And this is really how modern day AI is able to visually understand nearly everything that we can visually understand. So the core idea here is that deeper layers are learning, more complex features, right? Like the first layer was learning simple things like vertical and horizontal lines. The second layer might be learning things like corners. And, as we get deeper and deeper, we're starting to learn, what a car looks like, what a human space looks like, okay? So there's actually a really cool paper that kind of visualizes this concept that we just discussed. And you can see the paper down here, Zeeler and Fergus, 2014. So you can see that, here we're in layer 2, a relatively early layer. And you can see what I mentioned, we're actually, detecting things like corners, maybe a circle. We're seeing some circles, we're seeing some curves. So still relatively simple features. Then we move on to layer 3. And now we're starting to see patterns of shapes, more complicated features. We're even starting to get tires maybe, these look like tires kind of. And here you can see the silhouette of a human clearly. And yeah, in our deepest layers, now we're starting to get things like dog faces. We're visually understanding what a dog looks like or what an eye looks like. Complex features, the deeper we go into our net. Okay, so we mentioned parameters that control how much we move the kernel by. That parameter is called stride, right? So in our example, we kind of arbitrarily decided to just move by 1 earlier, right? 1, 2, 3, 4. But that was with a stride of 1. So with a stride of 2, what we would do is this would be our first computation, and then we'd move by 2. But you can see some of our values are actually multiplying by none, which is not good. So that problem of bleeding off the edge of the image introduces a parameter called padding. And padding is where you add a bunch of padding around the edges of your image to enable complete valid calculations or convolutions. And you can control how much padding you want. So here we're going to do 1 layer, and what kind of padding you want. Okay? So we're going to be adding 1 layer of 0 padding all around our image. So you can see these values here, all around our original image, which was this 3x3 image here. Okay? And remember, this problem was caused by us attempting to do a stride of 2. So let's see if we can do it now. Okay, so we have our kernel, and you can see now we can do a stride of 2. And we have values to do that with. We even have extra padding values on the right and bottom that we're not using, which is totally fine. So 1 convolution, 2 convolution, 3 convolution, 4 convolution. Okay? A stride of 2. And by doing that, we get our activation map. Okay? Right here. So this formula will tell you what activation map size output to expect from, all the input sizes and parameters that you're using. So we simply take our original height of our image, which is 3, and we plug it in here. So height of image, you can see. And then we subtract the kernel size, which is 2. We add it to 2 times our padding size, which is 1, if you remember. And then we divide all that by stride. And then we add 1 to that result. And this division will actually be a floor division here, which is why, we don't want fractions, right, in our output size. We always want whole numbers. And so you can see that we do indeed get an output height of 2, which matches what we actually got here.